Now let us discuss practical bias detection workflows. A robust workflow starts before model training. You examine dataset composition. You compute representation ratios. You ask whether certain groups are underrepresented. You inspect feature distributions across groups. You identify potential proxy variables. Next, during model evaluation, you compute performance metrics per group. You visualize disparities. You look for statistically significant gaps. You analyze confusion matrices separately for each group. This is not a one-time step. It must be integrated into continuous integration pipelines. In more advanced settings, you perform intersectional analysis. Instead of analyzing gender and race separately, you analyze combinations, such as women of a certain ethnicity. Bias can be hidden at intersections. A model may appear fair when evaluated separately across gender and race but show disparities when these attributes are combined. Fairness metrics also extend beyond classification tasks. In ranking systems, you might evaluate exposure fairness. Do certain groups consistently receive lower positions in ranked lists? In recommendation systems, you might analyze whether content from certain creators receives systematically less visibility. In generative models, bias detection takes different forms. You may prompt a language model with similar inputs that differ only in demographic cues and analyze output sentiment or content. You may test image generation systems to see whether certain professions are stereotypically associated with certain genders or ethnicities. Mitigating bias requires interventions at multiple levels. Pre-processing techniques modify the data before training. This might involve reweighting samples so that underrepresented groups have more influence during training. It might involve removing or transforming features that act as proxies. In-processing techniques modify the training objective. You can add fairness constraints or penalties to the loss function to reduce disparities in error rates. This requires careful engineering to avoid destabilizing training or degrading performance excessively. Post-processing techniques modify the model outputs after training. For example, you can adjust decision thresholds separately for different groups to equalize certain metrics. While effective in some cases, this approach can raise concerns about explicitly using protected attributes at decision time. There is always a trade-off between fairness and other performance metrics, but the relationship is not always zero-sum. Sometimes bias reduction improves generalization because the model is forced to learn more robust patterns rather than overfitting to spurious correlations. Monitoring fairness does not end at deployment. Models operate in dynamic environments. Data distributions shift. A system that was fair at launch can become biased over time due to population changes or feedback loops. Therefore, fairness metrics must be tracked continuously, just like accuracy and latency. From a governance perspective, fairness requires documentation and transparency. Model cards and data sheets are tools used to describe intended use, training data characteristics, evaluation procedures, and known limitations. Documentation does not eliminate bias, but it makes risks explicit. It is also important to distinguish between allocative harm and representational harm. Allocative harm occurs when resources or opportunities are distributed unfairly. Representational harm occurs when systems reinforce stereotypes or degrade the dignity of certain groups, even if no direct resource allocation is involved. Both forms are relevant in AI systems. Let us reflect on the relationship between fairness and explainability. If a model is opaque, detecting bias becomes harder. Explainability techniques such as feature attribution can help identify whether sensitive attributes or their proxies are influencing predictions. However, explanations themselves can be misleading if misinterpreted. Fairness is also linked to robustness. Adversarial attacks can exploit fairness constraints. Conversely, fairness interventions can sometimes reduce robustness if they introduce additional complexity. Designing systems that are both fair and robust is an open research challenge. Another advanced topic is the tension between privacy and fairness. Collecting demographic data is often necessary to measure disparities. But collecting such data can raise privacy concerns. In some jurisdictions, it may even be illegal to use protected attributes in decision-making. This creates a paradox. You need demographic information to detect bias, but you may not be allowed to use it. There is also the question of global versus local fairness. A model may be fair on average but unfair in specific regions or subpopulations. This is especially relevant in geographically distributed systems. From an architectural standpoint, fairness considerations should be integrated into system design from the beginning. Instead of treating fairness as an afterthought, you embed fairness checks into data pipelines, training loops, and evaluation dashboards. You treat fairness metrics as first-class citizens. For technical audiences like you, the key mindset shift is to treat fairness as a measurable system property, not as an abstract ethical slogan. Just as you would measure throughput, memory consumption, and accuracy, you measure disparities. You track them over time. You set acceptable thresholds based on domain requirements. However, measurement is not enough. You must interpret metrics carefully. A disparity does not automatically imply unjust discrimination. It may reflect underlying structural inequalities. Conversely, the absence of disparity in a chosen metric does not guarantee fairness in a broader moral sense. Therefore, fairness engineering is an interdisciplinary practice. It requires collaboration between data scientists, domain experts, legal advisors, and ethicists. Engineers must understand legal frameworks such as anti-discrimination law, but also the social context in which systems operate. Let me conclude with a structural summary. Bias in AI models originates from data, labeling, modeling choices, and deployment dynamics. Detecting bias requires disaggregated analysis, multiple fairness metrics, and intersectional evaluation. Fairness metrics include demographic parity, equalized odds, equality of opportunity, predictive parity, individual fairness, and counterfactual fairness. These metrics are often mutually incompatible when base rates differ, forcing normative choices. Mitigation strategies can be applied before, during, or after training, and fairness must be monitored continuously in production. Your responsibility is not only to optimize performance but also to understand the societal impact of the systems you build. Fairness is not a constraint imposed from outside engineering. It is part of building reliable, trustworthy, and responsible AI systems. If you approach fairness with the same rigor that you apply to model optimization, you will contribute to systems that are not only intelligent, but also aligned with human values.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.